Good morning everyone, welcome back for the second time in the module number 7 where we are talking about the vapor power cycle. In the previous lecture, you were introduced to the concept of the ideal Rankine cycle, which you can say is the most popular and universally adopted cycle for steam power generation. In any kind of steam power plant, whether that is thermal based or nuclear based, but Rankine cycle or modified and adopted version of the Rankine power cycle, vapor power cycle is the one that is universally followed. Now, in the previous lecture, you were introduced to this particular concept of Rankine cycle, where we have seen that Rankine cycle is a vapor power cycle, that is it involves the change of phase from liquid to vapor phase and vapor to liquid phase both, that is it involves both evaporation and condensation processes. And generally the cycle comprises of 4 processes, the ideal cycle at least, where 2 of them are isobaric in nature, isobaric heat transfer processes. One is heat addition, that is evaporation, another is heat rejection, that is condensation, and it also involves 2 isentropic processes, one isentropic expansion in the turbine and one isentropic compression in the pump. And the major difference that you must have observed by now of the Rankine cycle with the Brayton cycle is in this particular process. Of course, both Rankine cycle and Brayton cycle involves 2 isobaric heat transfer processes and 2 isentropic processes. However, there are 2 major differences. One, in case of Brayton cycle, our working medium is gas, that is for all the processes the temperature level remains well above the critical point of the corresponding substance, and therefore, it is always treated as a gas. We can treat this as an ideal gas or maybe real gas, whatever, but that is gaseous in nature. However, for a Rankine cycle, though we have the same 4 processes, but here the temperature level is below the critical point, therefore, we have the phase change involved. And the second big difference, which actually is associated with the first one, is in this particular process. Here the compression part is done entirely with the liquid state. Now, we know that the work input requirement for the compression process is proportional to the specific volume. In the Brayton cycle, as the working medium is gas with very high specific volume, so we have to go for something like intercooling and multi-stage compressions, etc., in order to reduce the compression work by maintaining a constant temperature or low temperature. However, here the working medium is liquid. At the end of condensation, invariably the state of the working substance is that of saturated liquid, that is the state point 3, and then we are doing the entire pump operation in the subcooled or compressed liquid zone, and the liquid stage or liquid phase being incompressible nature, corresponding specific volume being very low. Therefore, the work input requirement for the pump generally is extremely low. We have already seen that the work input requirement for the pump can often be calculated as minus integral V dP, which invariably reduces to V into the difference between the boiler pressure and condenser pressure, because there is hardly any change in the specific volume from state point 3 to 4. And when we are working with water, for water this V is invariably of the order of 0.001 meter cube per kg, as long as we are dealing with normal pressure levels. Unless we are going to something very close to the critical pressure, specific volume for liquid water will remain in that zone only. I should say write Vf, and therefore, this pump work, whatever may be the pressure difference between the boiler pressure and turbine pressure, this pump work remains extremely small. So, though the turbine, the level of work produced by the turbine may be quite similar between the Rankine cycle and the Brayton cycle, however, the pump work, that is the back work, is extremely small, thereby giving very high net work output and work ratio, and very small, negligibly small back work ratio. Now, the ideal Rankine cycle of course can have 2 variation, as shown here. We have already discussed about both of them. In one case, in this one we call it the Rankine cycle with wet steam, because at the inlet to the turbine the state of the working medium is that of vapor, and the entire expansion in the turbine is done within the vapor dome, that is starting from saturated vapor to a saturated liquid vapor mixture. In the second case, at the entry to the turbine, the state of the working medium is that of superheated vapor, So, the entire expansion state can be done on entirely on the vapor side, that is like as shown in this particular diagram, starting from superheated vapor to saturated vapor, or sometimes we may have this expanded a bit more into a mixture zone coming somewhere here, that is major part done in the major part done in the superheated vapor side and only a small portion in the mixture side. And the major advantage of this superheating is in twofold. One, we are able to increase the maximum temperature of heat addition, that is the maximum cycle temperature, which we shall be seeing the advantage of that one shortly. And the second advantage is here, like in case of wet steam, the quality at this point number 2, your X2 can be quite low, which is much higher with superheated vapor. And in practical operation, we would always like to keep this x2 to be greater equal to 0.88 in order to avoid the erosion related issues. So, superheating definitely helps in that point of view. Now, both these cycles are ideal cycles, that is where we are not considering the irreversibilities which can be present in the compressor and pump, and also the pressure drop which the fluid may experience while passing through the boiler or the turbine, boiler or the condenser. The effect of isentropic efficiency we have seen through a numerical example. Let us see the effect of all such possible practical difficulties in another one. We are solving several numerical problems in this module in order to show you the magnitude of the effect that we are talking about. Here we are looking to identify the thermal efficiency and net power output from a steam power plant operating on a Rankine cycle with a mass flow rate of 15 kg per second, and this is the cycle. Now, look at this. If we start from point number 1, which is here at the inlet to the pump, the pressure is 9 kilopascal. At the exit, it has been increased to 16 megapascal, but the pump has an isentropic efficiency of 0.85. So, there are irreversibilities. Secondly, look at this, 16 megapascal is the pressure at the outlet of the pump, but when the liquid water gets transferred from the pump to the boiler through the pipeline, because of the frictional effects, there is some loss in pressure and it enters the boiler with a pressure of 15.9 megapascal and 35 degrees Celsius. Remember, the temperature which is not given, temperature at the exit of the pump may not be 35 degrees Celsius, may not be 38 degrees Celsius also, it can be anything else, we do not know that information. Now, in ideal cycle, like shown in this diagram, in the ideal cycle, both the heat addition in the boiler and heat rejection in the condenser are done at constant pressure. But look what we are having here. At the inlet to the boiler, the pressure is 15.9 megapascal, at the exit the pressure is 15.2 megapascal. So, there is 0.7 megapascal pressure loss while the fluid passes through the boiler, but it comes out with a temperature of 625 degrees Celsius and proceeds to the turbine. Let me get the TS diagram into picture also. Look at the diagram. Here point number 1 is the state before the pumping operation starts, and had the pump being a perfectly reversible one, so it should have reached point number 2s, but because of the presence of the irreversibilities, that is that 0.85 isentropic efficiency, it reaches 0.2. Up to that part is fine because we have already encountered this. But when the fluid passes from pump exit to the boiler, there is further pressure loss, because of which it comes down to this particular 0.3. So, 2 is the exit state of the pump, that is your pump operation is associated with the process 1 to 2. However, the boiler operation is associated with not 2, but it starts from 0.3 and proceeds to 0.4, and this is your point number 4. Had the had the fluid entering the boiler with the same pressure of 16 megapascal, that is there is no pressure loss, then it would have ended up somewhere here. But this particular line is the 16 megapascal line, and this line is that 15.9 megapascal line. So, there is a change in the location of 0.4, and once it comes out of the boiler, then it again has to pass through some pipelines to reach the turbine. So, there is a further drop from this 0.4 to 0.5, and the turbine operation does not start from 0.4, rather it starts from 0.5, which has this particular rating 15 megapascal, that is there is a 0.2 megapascal drop. So, the fluid enters the exits the pump at a pressure of 16 megapascal and enters the turbine at a pressure of 15 megapascal. So, there is one full megapascal pressure drop from pump exit to the turbine inlet, which is definitely huge loss, a significant loss in exergy or work potential. Now, the pumping operation proceeds from 5 to 6. Had the the turbine expansion, had the expansion been isentropic, you should have reached 0.6 s, but we are reaching point number 6 because the turbine has an isentropic efficiency of 0.87. Then generally turbine exit is directly connected to the condenser. So, there is no pressure loss to be considered or significant pressure loss to be considered. So, the steam or mixture is able to enter the condenser with that same pressure of 10 kilopascal, then it proceeds to the condensation process and reaches this point number 1. And look at this, 10 kilopascal is the pressure at the condenser exit, and when it enters the pump, it enters with 9 kilopascal. So, 1 kilopascal pressure loss is also present in the condenser side. So, let us try to see the effect of these irreversibilities. If we want to see the effect of this in ideal scenario, let us try to work out. In ideal scenario, the pump work should have been V into pressure at point number 2 minus pressure at point number 1, that is double naught 1. You can calculate the exact specific volume of corresponding to this 9 kilopascal and 38 degree Celsius, but that will be coming in that order only, into the exit pressure from the pump is 16 megapascal. So, 16 to 10 to the power 3 kilopascal minus 9 kilopascal. So, this is the work output that we should have provided to the pump had that been perfectly reversible, but because of the presence of irreversibilities, the pump work requirement in actual will be equal to this theoretical value divided by eta pump, which is 0.85, and if you put the numbers, this will be coming approximately 19 kilojoule per kg. So, this is the pump work requirement. Similarly, the turbine work that we should have got in this case, turbine work per unit mass flow rate, that should have been H6s minus H5 had there been this been an isentropic process, but in this particular scenario, or actually I have written it opposite, it should have been H5 minus H6s, but because of the presence of irreversibilities, the actual work that the turbine is producing is the efficiency for the turbine into H5 minus H6s. Now, to calculate H5, the state is given as 15 megapascal and 600 degree Celsius. So, you can this is generally superheated. So, you can directly get the value of H5, and then you can also get the value of entropy corresponding to this, and using that you can identify the location of 6s. So, from there you can calculate the turbine work. See, this 10 kilopascal is provided as an information about the point number 6, but no information is given about the quality. So, we can't get the value of H6 directly, we have to use the efficiency for the turbine. So, this value in this particular case I have worked out to save some time, 1277 kilojoule per kg. Now, the heat input requirement in the boiler, what will be your QB? So, the exit state of the boiler is H4, inlet state is H3, and all informations are given. Point number 4 corresponds to 15.2 megapascal and 625 degree Celsius. Point number 3 corresponds to 15.9 megapascal and 35 degree Celsius. So, if you put the numbers, you are going to get 3487.5 kilojoule per kg. So, the thermal efficiency should be equal to W net by QB, where your W net is the turbine work minus the, or I should write the turbine work in actual minus the actual pump work divided by QB, and in this case it will be coming something around 36.1%. We have not calculated the condensation heat in this case, but you can easily calculate also using the information from point 6 and point 1, or there is an alternate way also. We have got the efficiency, and you know that the thermal efficiency can also be written as 1 minus QC upon QB. Now, you know thermal efficiency, you know QB, from there also you can easily calculate total amount of heat rejected in the condenser. And the second information, we have to calculate the net power output. Now, the mass flow rate is given as 15 kg per second. So, the W dot net should be equal to m dot into small w net, that is m dot into the actual turbine work output minus actual pump work input, and putting these values, it will be coming something like 18.9 megawatt. So, once there are so many kind of irreversibilities and irregularities present in the system, this is an approach by which we can tackle this, but we need much more information than the ideal cycle. We need to have proper information about each of the points. So, had there been an ideal cycle, this 16 MPa pressure should have been prevailed at all this point 2, 3, 4, 5, etc. We do not needed to have all other 3 pressure informations, but here as the pressure is varying, so we need to know pressure at all these 3 points. Now, let us move on to check out what are the ways we can improve the efficiency of a Rankine cycle. This is the standard diagram for a Rankine cycle without any irreversibilities or pressure losses. Now, look at this diagram, it is a TS diagram. So, during the heat addition process, the temperature of the fluid starts from temperature T2 and moves on to temperature T3, whereas during the heat rejection process, in ideal cycle the temperature remains more or less uniform, which is T4 and or T1, both of them are equal. So, the temperature of heat rejection is a constant, but heat temperature varies during heat addition, and therefore, the average temperature corresponding to, I should write the average temperature corresponding to heat addition is significantly lesser than the maximum temperature T3, a maximum cycle temperature. Now, if we compare this one with a Carnot cycle, we know that for a Carnot cycle, the thermal efficiency is given as 1 minus temperature at which heat reaction takes place minus temperature at which heat addition takes place. And if we assume that if the temperature is varying during the cycle, like in case of a Rankine cycle, then from where we can draw an implication that the thermal efficiency for a Rankine cycle should increase, or if we want to increase the efficiency, we either have to increase the average temperature corresponding to heat addition, or we have to reduce the average temperature corresponding to heat rejection. Now, in this particular cycle, the average temperature corresponding to heat rejection is a constant, because temperature is not varying, but somehow if we can reduce this temperature even further, we should have got an increase in thermal efficiency. And on the heat addition side, there is a lot of scope of improvement, because there is significant temperature variation from T2 to T3, and therefore, we should try to put some effort by which we can increase the average temperature of this heat addition, then only we can achieve some increase in the efficiency or work output of the Rankine cycle. So, let us explore a few options. The first option is try to increase the boiler pressure. Look at this, 2 Rankine cycles are shown. One cycle is this 1, 2, 3, 4, 1, and the second cycle is 1, 2 prime, 3 prime, 4 prime, 1. And in both the cases, the maximum temperature is constant, maximum cycle temperature is constant, the condensation temperature or condenser side pressure, that is also constant. Only thing that deviates between these two cycles are the pressure on the boiler side. Let us say this particular pressure we term as PB1 and the second one we term as PB2. So, clearly your PB2 is greater than PB1. Then look at what we are getting from diagram point of view. The portion that is shaded in grey, that corresponds to only the cycle 1, and the portion shaded in pink, that corresponds to only to the cycle 2. Now, the area enclosed by this cycle in TS plane corresponds to the net heat interaction, that is cyclic integral of del Q, And as per the first law of thermodynamics for a cycle, we know that this also has to be equal to cyclic integral of del W, that is the net work output that we can get from this cycle. Therefore, area enclosed by this curve on the T s plane, or area enclosed by this cycle on the T s plane, is also an indication of the net work output that we could have got. And now, once we are moving from the first cycle to the second cycle, that is we are moving to a higher boiler pressure, the one shaded in grey, that is the portion that we are losing now. So, that amount of work output will decrease, but the one shaded in pink, that is a new addition. So, that is an increase in the net work output. And though it is quite difficult to understand from this diagram, but it can be shown that the one shaded in pink, that area is at least even maybe by a smaller amount, but is still higher than the area enclosed by the or shaded in the grey. There is another way of showing this. If we compare these cycles, the temperature corresponding to heat rejection remains the same. Now, which cycle has a higher average temperature for heat addition? If say T A average for cycle 1 and T A average for cycle 2, which one is higher? Just from the first one, this particular one varies from 2 to 3, this particular one varies from 2 prime to 3 prime, or 3, because 3 and 3 prime both are same, 3 prime. So, we can say that this varies from 2 to T max, and this one varies from 2 prime to again to T max. So, the maximum temperature is same. What about the minimum temperature? 2 prime definitely is T2 prime definitely is higher than T2. Therefore, the average temperature of heat addition corresponding to the second cycle definitely is greater than the same corresponding to the first cycle, and so we can say that the efficiency corresponding to the second cycle, or at least the work output that we are going to get from the second cycle, definitely will be higher. Efficiency for this cycle 1 also will be lesser compared to the efficiency for the cycle 2. So, the first option of increasing the thermal efficiency for a Rankine cycle is to increase the boiler pressure. Of course, one shortcoming that we are also getting, if we look at the turbine exit position, as we are increasing the boiler pressure, maintaining the condenser pressure the same, the point 4 is shifting inwards, that is towards lower quality side. So, the turbine exit quality is reducing, and therefore, there will be added problem with erosion. There is another practical difficulty also, as we are going to higher pressure levels, then the tubings and shells that you are going to use for your plant, they has to withstand much higher pressure, and so you may need much costlier materials. But the bigger problem is the reduction in the turbine exit quality. So, the increase in boiler pressure gives you the advantage of an increase in the efficiency and net work output, but that causes a reduction in the turbine exit quality, which is an disadvantage. In the modern times, in an effort to increase the boiler pressure, we have also been able to reach the supercritical pressure level, where the boiler pressure is actually greater than the critical pressure of the corresponding substance, and therefore, we are actually not going for any exclusive phase change, we are just moving from point 2 to point 3, almost like a single phase heat addition, which has its some advantage of its own, but of course, we have to deal with much larger pressure. Like the critical pressure for the for water is 22.1 megapascal. So, if we want to operate with a supercritical pressure level, we have to go to something like 250 bar or even higher, which is a significant pressure to deal with. Still, the supercritical power station is definitely on and is a very active area of research, and has also been implemented in certain locations. Now, option number 2, increase in the maximum temperature. Of course, if we increase the maximum temperature, our direct gain will be in the average temperature of heat addition, like shown in the diagram. Here again we have two cycles, 1, 2, 3, 4, 1, and 1, 2, 3 prime, 4 prime, 1, and between these two cycles, boiler pressure and condenser pressure, they are constant. Now, as the pressure remains constant, the effect of increase in the maximum temperature is a direct increase in the area enclosed by the T_S curve, and therefore, an increase in the work output. So, the average temperature of heat addition corresponding to the cycle 2 is definitely greater than the average temperature corresponding to the average temperature of heat addition corresponding to cycle 1, because in both cases we are starting heat addition at point 2, but we are finishing at different points, the second cycle finishing at a higher temperature, and accordingly the efficiency for the second cycle, thermal efficiency, will definitely be greater than the first cycle. So, increase in the maximum temperature definitely is a potent option. Also look what is happening on the turbine exit. The exit point is getting shifted towards right, that is the exit quality is also increasing, it is approaching the superheated vapor. Therefore, here we are gaining from both point of view, we are getting higher pressure and also we are getting higher turbine exit quality, both of which are highly desirable. So, compared to the increase in the boiler pressure level, probably this can be a better option, because we are gaining in two fronts. But definite problem is we have to deal with, the material has to deal with higher temperature levels, and therefore, there will be certain kind of metallurgical limits. The third option is on the condenser side. Here we are maintaining, again we are going for 2 cycles, 1, 2, 3, 4, 1, and the second cycle is 1, 2 prime, 3, 4 prime, 1 prime. Between these two cycles, the change, the thing that is changing is the condenser pressure and accordingly the temperature of condensation, temperature corresponding to condensation, but the maximum temperature and the boiler pressure, they are constant. Now, once we are expanding in the turbine to a lower pressure level, then definitely the exit state is getting shifted to a lower point and there is a significant increase in the area that has been enclosed by the curve. Also, as the condensation temperature is decreasing, so though there is no change in the average temperature corresponding to heat addition or hardly any change, we have the average temperature corresponding to heat rejection that is decreasing. As per this diagram, you can see that the heat addition process is also starting from a lower point T2 prime instead of T2. So, the average temperature corresponding to heat addition is also decreasing, but this decrease may not be significant compared to this particular decrease, leading to an overall increase in the thermal efficiency. So, there are three ways of increasing the thermal efficiency of a Rankine cycle. First is the boiler pressure, where we have the disadvantage of a loss or reduction in the turbine exit quality, then an increase in the maximum temperature where turbine exit quality is also increasing, and the third is a reduction in the condenser pressure, but what happening to the exit quality? The exit point is getting shifted towards left or towards higher quality side, or I should say lower quality side. So, again here we are having a low quality mixture at the turbine exit, so erosion problem will be there. So, this particular option of decreasing the condenser pressure comes with a problem of reduction in the turbine exit quality and also a practical difficulty, that is we are generally the pressure maintained inside the condenser is well below the atmospheric pressure, because we select the condensation pressure based upon the atmospheric temperature. Now, you know that for water the atmospheric corresponding atmospheric pressure, the saturation temperature is 100 degree Celsius. Then if we want to attain condensation say at a temperature of 20 degree Celsius, we have to reduce the pressure significantly below that atmospheric pressure. So, the condenser is already operating under vacuum condition and there is every possibility of air leaking from surrounding into the condenser and thereby hampering the heat transfer performance. And now, if we reduce the condenser pressure even more, so higher condensation vacuum will be required, which will put additional burden from maintenance and fabrication point of view. But still all three options can be exercised. Generally we like to then if we summarize, then we always like to have a higher boiler pressure as much as your material can withstand, and also as long as the turbine exit quality is manageable. We want a higher maximum temperature as long as your metallurgical limits are adhered with, and we want a lower condensation pressure as long as you can maintain the vacuum inside the condenser, and also again the turbine exit quality is manageable. So, all three or the combination of all three or any two of them are quite often used in industries. We would like to show the effect of each of them through this numerical example. Here we are talking about a steam power plant operating on an ideal Rankine cycle. Steam enters the turbine at 3 megapascal and 350 degrees Celsius and is condensed at a pressure of 10 kilopascal. So, this is a cycle, very standard cycle shown here. Let us try to calculate the thermal efficiency for this plant. Superheating is there, but none of the options that we discussed about has been explored here. So, let us see, point number 1 corresponds to a pressure of 10 kilopascal and a quality of 0 because it is saturated liquid. So, corresponding to this, if we check from the table, your H1 is 191.81 kilojoule per kg, and specific volume at this particular point is 00101. Look at this magnitude. This is I am taking directly from the table which is kept beside me, and the value is that 001 that we used earlier also. Now, point number 2 corresponds to a pressure of 3 megapascal and no other informations are given, but assuming the compression process to be isentropic, then we know that S2 equal to S1. But this information we generally do not need to make use of, because we can directly calculate the pump work using this specific volume at point 1 into the difference between boiler pressure and condenser pressure. So, it is 00101 into the boiler pressure is 3 into 10 cube minus the condenser pressure is 10 in terms of kilopascal. So, the turbine work is coming a meager value of 3.02 kilojoule per kg, and from there we can calculate H2 to be equal to H1 plus the pump work. So, a minor change into have 194.83 kilojoule per kg. So, point 1 and 2 have been identified. Now, move to point 3. Point 3 clearly given to be superheated, it is 3 megapascal and 350 degree Celsius. So, we have from that superheated table we have H3 equal to 3116.1 kilojoule per kg, and entropy we need here, we need entropy which is 6.745 kilojoule per kg, and point number 4 we know it to be at a pressure of 10 kilopascal and S2 to be equal to S3 to be equal to S4. And now, if we compare the values for this S4 is coming to be greater than the SF corresponding to the condenser pressure, but less than Sg corresponding to the condenser pressure, which indicates this S4 is in the mixture dome. Though the diagram is indicative, but you always need to check this way, as this S4 is coming between SF or Sg or not. If it is greater than Sg, then what will happen? It is on the superheated side. If it is less than SF, then it is on the subcooled side, which hardly happens. But if it is in between the two, it is on the mixture side. So, if you put the numbers, then you will be getting your X4 to be equal to 0.8128, 0.8128, which is a significant number. We need to make a note of this number. Turbine exit quality for this configuration is 0.81, and from there we can compute your H4 to be equal to HF corresponding to PC plus X4 into HFG corresponding to PC, and H4 will be coming as 2136.1 kilojoule per kg. So, we can easily calculate the remaining numbers. The QB, we have to calculate the thermal efficiency. So, your QB will be equal to H3 minus H2, and this is coming to be 3488 kilojoule per kg, and condensation heat rejection or heat rejection is coming to be equal to H4 minus H1, which is 2188.5. which gives you a thermal efficiency of 1 minus QC by QB to be equal to 33.4%. Sorry, I have given wrong numbers. I messed up with another one. So, here it is will be coming as 2921.3 and it will be coming as 1944.3, and correspondingly the thermal efficiency will be coming 33.4%. So, this is about the first case where we are talking about an ideal cycle. Now, look at this. Here the steam is superheated to 600 degree Celsius, rest remains same. So, this is the situation. Here point 1 and 2 are same. So, 1 and 2 are same. Accordingly, there is no change in the calculations of H1, H2 and the pump work. Of course, we have not calculated the turbine work in this problem. If you want the turbine work, you can also calculate to be as H3 minus H4. That is not required in our case for our demonstration. So, I have not shown here, but you can also calculate this number. So, 1 and 2 remain same, but 3 there is a change. So, point number 3, what is happening? Here the condition is that of 3 megapascal and 600 degree Celsius. So, correspondingly your H3 will be coming as 3682.8 kilojoule per kg. Your S3 will be coming as 7.5103 kilojoule per kg Kelvin. For point number 4, the pressure is same, which is 10 kilopascal, and S4 equal to S3. Putting this information, you will be getting here X4 to be coming as 0.915, using which we shall be getting H4 to be equal to 2380.3 kilojoule per kg, giving you so correspondingly we have, I am just directly noting the numbers to save some time. QB is equal to H3 minus H2, which is 3488.0 kilojoule per kg. QC is equal to H4 minus H1, which is 2188.5 kilojoule per kg. Combining this, the thermal efficiency will be coming as 37.3%. Now, a few things to compare. Here we have just increased the maximum temperature without affecting the boiler and condenser pressure. Then first note this, in the previous case our boiler exit quality was 81%, here it has gone to 91%. So, significant increase, sorry, turbine exit quality, there is significant increase in the turbine exit quality. And what about thermal efficiency? It was 33%, now it has gone to 37%. If you compare the boiler heat addition and condenser heat rejection, boiler heat addition has increased quite a bit, condenser heat rejection has also increased, but to a lesser amount degree, giving you a higher increase in the thermal efficiency. So, we are gaining both front, thermal efficiency has increased and also the turbine exit quality has increased. Now, the second part, the boiler pressure is raised to 15 megapascal and turbine inlet temperature is maintained at 600 degree Celsius. So, boiler pressure now goes from 3 megapascal to 15 megapascal. So, point number 1 again remains the same, but others have changed. Pump work in this case will be equal to V1 into the boiler pressure minus condenser pressure, that is 0.0101 into, here the boiler pressure is now 15 megapascal. So, it is 15 into 10 to the power 3 minus 10. So, the pump work increases to 15.13 or rather 14 kilojoule per kg. So, there is a small increase in the pump work. Accordingly, we can calculate H2 to be equal to H1 plus pump work. I am not calculating the numbers, just showing you the way, because you by now you know how to get this. Then point 3 now corresponds to 15 megapascal and 600 degree Celsius. Using this, you can get the value of H3 and S3 from the table. Point number 4 corresponds to the same pressure of 10 kilopascal and S4 is equal to S3. If you combine that, you are going to get in this case to be x4 equal to 0.804. So, boiler pressure has increased, maximum temperature remains same and it has come down from this 0.915 to 0.804 because of the increase in the boiler pressure. Maximum temperature and condensation pressure remains the same. And if you calculate QB and QC, your thermal efficiency will be coming to be equal to 43% approximately. So, though there is a reduction in the turbine exit quality, there is a significant increase in the thermal efficiency. So, you may have to go for some kind of trade off. I would request you to solve the same problem by maintaining the maximum temperature as 600 degree Celsius, like in this problem, boiler pressure to be 15 megapascal and condenser pressure of 1 kilopascal, and calculate the thermal efficiency from this to see the effect of the condensation pressure. So, this is the way we can increase the performance or efficiency for a ideal Rankine cycle. But as we have seen, we can get higher efficiency by changing all these three options: boiler pressure, condenser pressure and maximum temperature. But if we want to increase both the efficiency and the turbine exit quality, our option is to only this maximum temperature, increase in maximum temperature. Now, maximum temperature theoretically we can keep on increasing, but as I have mentioned, there are metallurgical limitations, and so we may not be able to go to very high temperature. The 600 degree Celsius which we have used here is a quite decent practical limits. In fact, in India most of the power plant uses a maximum limit of 540 degree Celsius for metallurgical considerations. So, there is a second option, something that we have used in case of Brayton cycle also, where we go for multi-stage expansion and inclusion of reheating in between the multi-stage expansion. Just like what we have done in the Brayton cycle, here the steam that is coming from the boiler is initially expanded in a high pressure turbine up to some intermediate pressure level, as shown by this pressure here, the pressure P4. So, here this pressure P4 is less than the boiler pressure, but it is greater than the condenser pressure, somewhere intermediate, which is often called the reheat pressure also. And then at this point 4, this at this intermediate pressure, the steam is taken back to the boiler to reheat back to certain temperature. Generally it is heated up to the same temperature, but not essential to this. P5 can be equal to P3 or less than P3, or I am writing wrong. What I mean that the temperature at point number 5, that is T5, should be equal to T3 or less than T3. In no situation generally goes beyond T3, and then it is taken to the low pressure turbine where it is expanded to the condensation pressure up to this particular point. So, here we are expanding the steam in two stages of turbine, one is the high pressure turbine, other is the low pressure turbine. The concept of reheating with multi-stage expansion was introduced in early 1920s, but because of practical issues it was abandoned for about 15-20 years. Then in early 40s it started to operate again, where people started to use one stage of reheating. Later, after 1950s, people started using two stages of reheating. That is, instead of having two, we can have three turbines also. The first one is the high pressure turbine, where the expansion takes place from boiler pressure to first level of intermediate pressure. Then we have an intermediate pressure turbine, where the expansion goes from intermediate pressure 1 to intermediate pressure 2. Then we have the LP turbine, where expansion goes from the second intermediate pressure to the condenser pressure. If we keep on increasing the number of reheating, of course, we can almost maintain a near constant average reheat temperature, or rather I should say the reheat temperature remains almost constant to the maximum cycle temperature. Thereby, it's I should say, as the number of reheating increases, it tries to approach the maximum possible efficiency, but it is practically not at all feasible, because increasing the amount of gain in efficiency that we get by adding more than 2 reheat stages, that can't be justified corresponding to the cost that is incurred with this. So, hardly any cycle you will see which uses more than 2 reheat stage. Now, when you are using a cycle with a single stage reheat like this, then total amount of heat that has been added, the QB that we are using there, that has now two components. One is the primary one that we are using always, plus the reheat part. Now, we have. So, how much is the primary heating, which is H3 minus H2, and reheating part now H5 minus H4. So, this is the reheating part where the additional heat input will be required. And how much is your turbine work? Your turbine work now corresponds to the work produced by the HP turbine plus the work produced by the LP turbine. So, in HP turbine we are getting H3 minus H4, and in the LP turbine we are getting H5 minus H6. So, there will be increase in the total work output, but also there is increase in the total heat input requirement. So, it is difficult to say whether there at all will be any gain in the efficiency. In fact, because of reheating we may get some increase in the efficiency, we may get some reduction in the efficiency as well. And the change in efficiency with the adoption of reheating generally is not more than 1 or 2%, but the biggest gain is here. The turbine exit quality will be significantly higher compared to a single reheat case, or I should say a single stage turbine expansion. Also, generally the heat that is produced in the boiler, if we are not using any reheating, a significant part of that heat produced because of the fuel combustion may get wasted. So, we are also able to make better utilization of our resources by the reheating. One numerical example again can be considered just to demonstrate the effect of reheating. Here we are talking about a steam power plant operating in an ideal reheat Rankine cycle. Steam enters the high pressure turbine at 15 MPa and 600 degrees Celsius. So, here the point stage number 3 corresponds to 15 megapascal, which is the boiler pressure, and 600 degrees Celsius. So, from there we can easily calculate H3 and S3. I shall not be putting the numbers, I am leaving it up to you. And the condenser pressure is given as 10 kilopascal. The moisture content of steam at the exit of the low pressure turbine should not exceed 10.4%. That is your point number 6, your X6 should be greater or equal to 0.896, and in no case it should fall below this. So, what can be your maximum possible reheat pressure? That is, you have to calculate the pressure at this particular point 4, or I have to calculate pressure P4 or P5, which are same. Let us put X6 equal to 0.896. Then for point number 6, what we can say? We know that the pressure is 10 kilopascal, and we also know the value of X6. So, using this you can calculate the value of H6 and S6. Now, corresponding to the LP turbine expansion, S5 should be equal to S6, and for point number 5 we also know that the temperature at the inlet to both the turbines to be identical. So, we also know that T5 is equal to 600 degrees Celsius and S5 is equal to S6. If you combine these two, we can calculate P at point number 5, which is also P equal to point number 4, that is your reheat pressure. By using suitable use of the tables, we can identify this to be approximately equal to 4 megapascal. So, once we have this, corresponding to this we can calculate your H5, and now what to do with the rest part? Point number 3 you have already identified. So, let us come to the pump side. For point number 1, we know it is 10 kilopascal and quality equal to 0. So, from there you can get H1. Pump work will be equal to and V1. So, you will be equal to V1 into the boiler pressure minus condenser pressure. Your H2 will be equal to H1 plus the pump work. Q primary will be equal to your H3 minus H2. So, you can get the Q primary because H3 you have identified, and for point number 4 Now we know that point number 4, P4 is equal to 4 megapascal and S4 should be equal to S3. From there we have to identify, you can get your T4 to be coming approximately equal to 375.5 degrees Celsius. From there you can calculate H4. So, total QB will be equal to H3 minus H2 plus H5 minus H4, and W net will be equal to H3 minus H4 plus H5 minus H6. Combining this, your thermal efficiency will be coming in the range of 45%, but more importantly we are able to maintain a significantly high turbine exit quality. So, that is a demonstration of the reheat cycle, where with a single reheat we are able to get a decent thermal efficiency and also able to maintain a significantly high turbine exit quality. But as I have mentioned, we may not get any gain in the efficiency by adoption of the reheating. So, for that purpose, in order to ensure the gain in the thermal efficiency, we have to use something that again we have used in the Breton cycle, which is the regeneration. The detailed concept of regeneration I shall be explaining in the next lecture, but just to show you something, at point the heat addition is starting. This is a cycle shown without reheating, the standard Rankine cycle with superheat. We are starting heat addition at point 2, finishing heat addition at point 3. So, if we are supposed to heat this one, we are using a gas which is maintaining a constant temperature somewhat like this, then at this point the temperature difference is extremely high, whereas at this point the temperature difference is quite low, and heat addition with high temperature difference means lots of irreversibilities, lots of losses. Instead of using something like this, there are two ways we can do. If we can use a gas temperature profile something like this, that is in all cases the temperature difference between the combustion gas and the steam is not very large, then probably we can reduce the thermal efficiency, and secondly, or I should say reduce the irreversibilities, and secondly the heat that we are adding to the saturated liquid, that is between point 2 to 2 prime, if somehow we can manage this such that the steam or liquid water enters the boiler only at point 2 prime, then also the net temperature or average temperature corresponding to heat addition will correspond only to point 2 prime 2.3. So, there will be a significant increase in the average temperature of heat addition, and consequently we can expect gain in the thermal efficiency as well. So, the idea of regeneration is to adopt some means where we can raise the temperature of water from 2 to 2 prime before it enters the boiler. So, we would like to adopt some means where we can gain this much of change in the temperature of water before the steam enters the boiler, and that is what we refer as the regeneration, because there we shall be using certain means that I shall be explaining in the next class. This is one means, that is the first one, but I would like to go into the detail in the next class only, where we shall be explaining in detail about the process of regeneration, different kinds of regenerative heaters that we use, and consequently how much gain we can gain in the thermal efficiency. So, the advantage of having regeneration is the efficiency can theoretically be equal to the Carnot efficiency, but other two problems I will come back to this again in the next class. So, today we have discussed about the effect of boiler pressure, maximum temperature and condenser pressure on the performance of the Rankine cycle. The concept of reheat Rankine cycle was introduced and discussed in detail, and we have very briefly touched upon the concept of regeneration in the Rankine cycle. This is the point from where I would like to start my next lecture. So, please wait for that and try to solve a few numerical problems, so that you gain more exposure on the use of the reheat cycle. So, thanks for your attention. We shall be meeting again very soon. Thank you.